recap what we spoke about. We talked about the properties of arteries. Can anyone remember off the top of their head, what are some of the properties we talked about for our arteries? Can you remember any of the general properties we talked about that arteries have differently so far?
They have a large diameter.
Excellent. Yeah, so they've got a large diameter. And when we speak about diameter here, we're not talking about the lumen size. We're talking about the overall width of that vessel. That's because of that thick, smooth muscle lining. So they end up having a larger diameter. Anything?
They have little resistance.
Excellent. So the resistance here is very low. It's kind of the first branch right from the heart. And so we see very little resistance. Anything else about our large arteries in particular?
High elasticity.
So yep, they're high elasticity. And what does that kind of also translate to?
Low compliance.
Excellent, thank you. So they've got high elasticity, low compliance. Okay, so they are able to snap back, if you will, to their original shape, which allows them to be what do we describe them as being? Anyone remember?
Pressure reservoir.
Excellent, thank you. Yep, so a pressure reservoir. They have that ability to store pressure in the wall, and because they really want to snap back to that original shape, because of that low compliance, high elasticity, then we see that pressure being released, and that keeps flow constant throughout the cycle. All right, so let's keep going here and speak about arterioles. So I think we got to this slide, yes. So arterioles are going to be the more resistant vessels. This is where we see most of the resistance throughout the entire vasculature. It's also a part of the microcirculation, so it just means that the vessels here are smaller. We've talked about the venules, arterioles, and capillaries being a part of the microcirculation. It's going to be the branching point between our arteries and then our capillaries and meta-arterioles. It's got a ring of smooth muscle. It's got a thicker ring of smooth muscle, I'd say, and that's what's really going to regulate the radius. And we talked about the relationship between radius size and resistance. And so as we regulate the state of the smooth muscle in that arteriole, we can therefore regulate the radius, how wide or narrow that lumen is, and therefore regulate the resistance. Okay, so it's going to be one of the main areas of regulating the resistance that we see throughout the entire vasculature. Okay, so here we can see very nicely how the pressure drops off, or how the pressure changes as we move through these various branches. And so as we can see here at arterioles, this is where we see the largest drop off in our pressure. And so we see about pretty much most of the pressure drop off here. We also see the most resistance in these vessels, and that's why we see the major pressure drop off. The lumen of these vessels gets smaller, and so the resistance increases, and therefore the pressure drops off. So the largest pressure drop off and the greatest amount of total peripheral resistance is encountered here at the arterioles. And then we want to kind of compare that to what we saw in the arteries, right? The arteries being the first branch right from the heart. The resistance here is very low, right? They've got a nice large lumen, and we don't have as much regulation of the radius as we see in arterioles and the arteries. And so that's kind of a comparison there between the arteries and what we see in the arterioles. Now let's talk about how the arterioles change their state and therefore regulate the resistance by regulating the radius. So we talked about the last two mechanisms here, which are vasoconstriction. We talked about this idea that if the smooth muscle within the arteriole, if it relaxes, that's going to, if it constricts or contracts, that's going to decrease the size of the radius. In other words, increase the resistance. That idea is called vasoconstriction. And in terms of the images here on the right, that's going to be the second image. We also talked about the second phenomenon here, which is vasodilation. So if the smooth muscle there relaxes, that's going to increase the lumen or increase the radius, if you will, and that will allow for more blood to flow through, right? Decreased contraction, increased radius, more flow, less resistance. And so that would be the image at the bottom. So these are the two states of arterioles that we already talked about, but there's a third kind of mechanism of regulating the radius that we didn't really touch on, but we explored this idea last semester. So this is called arteriolar tone. Okay, arteriolar tone. And in this state, the smooth muscle is pretty much in its relaxed state. And so this is the inherent ability of these smooth muscle cells to have this slightly contracted state, even in the absence of any type of external or extrinsic regulation, okay? Does anyone remember the specific type of smooth muscle that we mentioned that has this tone, this inherent ability to be contracted without any stimulus? So we talked about
The heart.
well, the heart does have that autorhythmicity, but another type of smooth muscle. So we talked about two types of smooth muscle. One had that inherent ability to be contracted without any stimulus. So that would have been single unit smooth muscle. If you remember, that had lots of gap junctions. And so that was the basis for this type of state that we see in these smooth muscles around the vasculature. So these three mechanisms are what are used to regulate the radius and regulate the resistance. We've got that inherent tone, which keeps the vessel in this slightly contracted state, even when it's relaxed. And so really vessels are never really fully relaxed. They're always slightly constricted or contracted. We've also got the ability to vasoconstrict and then the ability to vasodilate. So these three mechanisms help us to manipulate the radius, help us to regulate the radius, regulate the resistance, and therefore regulate or manipulate the flow. Okay, and so what we can do is we can change the state of the smooth muscle that are lining these arterioles, which changes the radius. And that's how we control the blood that's flowing to different capillary beds, right? Remember, the arterioles are going to be the branching vessels in between the arteries and then the capillaries. And so it's going to be the opportunity that we have to manipulate or to regulate which capillary beds get more flow and which capillary beds get less flow by simply changing the radius of these arterioles. Okay. Now, the way that we regulate blood flow to different organs is pretty much based on need. How much need does this tissue or organ system, how much oxygen does it need? What metabolites are building up that need to be cleared away? And so we really look at the state of the tissues at the local level, and that's how we regulate how much or how little blood is flowing to that organ, okay? And so this is regulated by varying the resistance, right? That relationship that we just established. If we change the amount, if we change the state of the smooth muscle of these arterioles, we then change the radius and we then change the resistance. And so we want to remember this relationship as we talked about it. So we said that cardiac output is equal to mean arterial pressure divided by total peripheral resistance. That's kind of a systemic view or a more holistic view of that relationship, but we can also apply that relationship to a local level as well. And so the blood that's flowing to a specific organ, that's going to be equal to the mean arterial pressure divided by the resistance that's encountered within that specific organ as well. Okay, so we can think about it on a holistic level. We can also think about it at a more local organ level as well. Let's look at this schematic here. So what we're seeing is the heart. We've got the arterial pressure to three different organ systems, organ A, organ B, organ C, and then we've got the venous pressure on the opposite end. And what I want to point out here is that this is a closed system, right? So when we move blood to one organ or to another organ system based upon need, we don't magically create more blood in the system. What we do is we shunt blood from one spot to another. And that's really the importance of regulating the radius of the arterioles, is that it provides us the ability to shunt more blood to one system when we need it. Let's say we're fighting or fleeing from a threat, right? Under that fight or flight sympathetic nervous system influence, we need to shunt blood to, say, skeletal muscles or heart. And so what we simply do is vasoconstrict everywhere else and vasodilate to those arterioles, right? So that's how we regulate the flow to different organs, by simply changing the radius to various different capillary beds. Okay, here's another illustration to kind of illustrate that idea as well. So we've got two containers here. We've got 3 points of flow, or 3 conduits that are connecting here, A, B, and C. And so in this initial setup, we can see that we've got a pressure differential, which is giving us a flow rate in conduit A of about 1.5 liters per minute, about 50% of that flow. We've got a flow rate in conduit B about 1 liter per minute, which is about 33% of that total flow. And then we've got in conduit C, 0.5 liters per minute, which is about 17%. Now, I really want to drive home the point here that we cannot create more blood in the system. It's a closed system. We've got a maximum flow here of 100%. And so if we shunt blood, let's say to A or B or C, or we clamp down on the arteries that are flowing through, not arteries, but if you clamp down on conduit A or B or C, then we will we will move or shunt blood to the other systems as well. So let's look at another scenario or compare this here to another view. So what we see is that we've got the same amount of blood, okay? We now have a constriction through conduit B. So that decreased our percent of cardiac output from 33% on this previous slide here to now 20%. And so what that automatically means is that blood or that liquid needs to go somewhere else. And so what we see is that we now increase the percent of cardiac output in conduit A from 50% to 60% here. We also increase the flow in conduit C from 17% to 20%. So what this is really trying to stress is that we've got a closed system. We've got a set amount of cardiac output or bulk flow, if you will. And so in order to move blood to one organ system, we need to manipulate the radius of the capillaries to other organ systems by decreasing that radius. And then we can manipulate the radius that's going to the organ system we'd like to shunt blood to by vasodilating or increasing that radius. Okay. And now we'll talk about what we mean by need. So we talked about the state of the local tissues and how they may or may not need more blood flow. And so that will dictate or determine how we regulate the arterioles that are moving towards that organ. And so the local factors are what really control the vascular resistance, okay? It's gonna determine the state of the smooth muscle in that vessel wall. It's also going to regulate the radius and therefore determine how much flow is coming to the system, okay? Let's talk about what some of those local factors are. So they really are factors that are created or that change depending on the metabolic activity of the tissues. And so when we see an increased metabolic activity, we generally have vasodilation. And that just means that this tissue or this vascular bed or this organ system needs more blood. It's under increased metabolic activity. The cells are using more oxygen. They're producing more carbon dioxide. And so we need to increase the flow that's coming to that organ system. And the way that we do that is by, again, regulating the radius, relaxing the smooth muscle to those arterioles, and then vasodilating, causing more blood flow to come in. And some of the factors that would create this response are carbon dioxide, potassium, and hydrogen ions. And these are really just factors that, that tell us about the metabolic activity of these cells. So can anyone make a connection between carbon dioxide and the metabolic activity of cells? So how does carbon dioxide increase as tissues increase their metabolic activity? So think about where we make carbon dioxide. What are the processes that make carbon dioxide? So if you remember that cellular respiration, every time we break down glucose and we make ATP, carbon dioxide is made as a byproduct. And so this is telling us about the metabolic activity of cells. Likewise with potassium, right? Potassium is going to be pumped outside of the cell. Think about the sodium potassium pumps on the surface of all of our cells. And so as the metabolic activity of these cells, things like action potential, weights increase, we're pumping more potassium out of the cell. And so again, potassium is going to be an indicator of increased metabolic activity. How about hydrogen ions, which are acidic? How can we make a connection between the production of acid and metabolic activity? So if you remember us talking about muscle, the various types of muscle, and the way that muscles produce, specifically glycolic muscles, produce lots of lactic acid. And so that lactic acid is actually translated to hydrogen ions. And so that is going to be another indicator of increased metabolic activity, okay? So carbon dioxide levels, potassium levels, hydrogen ion levels, these are all indicators that the cells need more flow. They need more blood coming in to remove these metabolites, but also to bring in fresh oxygen, okay? On the flip side, we have changes associated with decreased metabolic activity. So if cells are well oxygenated, tissues are well oxygenated, they're getting enough perfusion, that is an indicator to vasoconstrict. And so excess oxygen levels is going to be the local factor that tells these arterioles we have enough oxygen, we have enough flow, you can go ahead and constrict that smooth muscle that's lining the arteriole. That's going to vasoconstrict the vessel altogether. That's going to decrease how much flow is coming to this tissue because obviously there's enough, okay? So factors like carbon dioxide, potassium, hydrogen is going to increase metabolic activity or are going to indicate increased metabolic activity and cause vasodilation, whereas oxygen is going to be the main indicator of decreased metabolic activity, and that's going to cause vasoconstriction.